Hi friends, now let's see what this reduction is. Reduction is a process which we convert one problem into another problem in polynomial time. So if we can do this conversion in polynomial time, then it would be much useful. So to understand whatever we are discussing now, let's use this graph. This graph has got a set of vertices 1, 2, 3, 4, 5, 6, and 7. And there are some edges connecting these vertices, and that is shown in the adjacency matrix here. Now, the first process we want to look at is to identify the independent set of vertices. Set of vertices which are called independent if they are not connected by any edge. Say if we select one as one of the vertex, then 2 cannot be used, 6 cannot be used, because 2 and 6 are connected to 1 by these two vertices. Therefore, neither 2 nor 6 can be used. Now, what can be used? So, maybe 7 can be used, because between 1 and 7 there is no such thing, no edge is there. And what else? So when 7 is used, 2 can't be used, 4 can't be used, then 6 is not possible, so maybe 5 we can use. So with 1, 2, 6 are disqualified, with 7, 2 and 4 are disqualified, with 5, 6 and 4 are disqualified. Now there is one more thing left which we can use as a 3. So 1, 3, 5 and 7 are the 4 vertices we have which are found to be independent. So that means if you look at 1, 3, 5 and 7 from this, so between 1 and 3 there is no edge, between 1 and 5 there is no edge, between 1 and 7 there is no edge, between 3 and 1 there is no edge, between 3 and 5 there is no edge, between 3 and 7 there is no edge, between 5 and 1 no edge, 5 and 3 no edge, and 5 and 7 no edge. Same way 7, 1 we don't have, 7, 3 we don't have, 7, 5 we don't have. So looking at this, we are now sure that 1, 3, 5, 7 are the 4 nodes. So that's a maximum thing we can think of. Any fifth node you try to add into this independent set, then it no longer remains independent. Say if you try to add 2, then this edge, this edge, this edge are a problem. Therefore, 2 can't be added. If you try to add 6, no, it can't be added. You try to add 4, no, can't be added. So neither 2 nor 4 nor 6 can be added. So that's these are the 4 vertices which we can call them as independent set. So the problem was simple, so we could manually solve it, and while doing so we have used our intelligence. We are seeing all the nodes parallelly, all the edges are visible parallelly, so we are working all these things in parallel and using our intelligence and lot more, and hence I think we could solve this in a limited time. But in reality, when machine is working, then machine is working with this, and then it has to look from A. If A is not connected to 3, then A is not connected to 4, A is not connected to 5, A is not connected to 7. So if 1 is selected, then I can select 3, I can select 4, I can select 5, I can select 7. So that way, if you just keep looking at that, so we can get some different possible independent sets, but the highest possible independent set would be 1, 3, 5, 7 only, and that's possible only with an algorithm which is of exponential time. Yeah, other side. We are given with these 4 nodes. Some magic had given these 4 nodes. Say that yes, these are the 4 nodes which are part of the independent set. Then it's time to verify. Is it right? Yeah, from 1 to 3 there is no connection, 1 to 7 there is no connection, 1 to 5 there is no connection, 3 to 5 there is no connection, 3 to 7 there is no connection, 5 to 7 there is no connection. So what did we do? So 1, 3, 5, 7. So we tried 1, 3, there is no connection, 1, 5, no connection, 1, 7, no connection. Then 3, 5, there is no connection, and 3, 7, there is no connection, and finally we verified 5, 7, there is no connection. So 1, 2, 3, 4, 5, 6 searches in this table will prove that these 4 are indeed independent set. So we could verify the answer in polynomial time, and hence this problem is in NP. Done. Now we were working on reduction. So what can we do? So next let me try. Can we use this information? Can we use this information to create vertex cover? So what is vertex cover? Vertex cover is one which we need to find minimum number of vertices so that all the edges are connected to these set of vertices. So how it can be done? So the one way, if you try to solve this directly, then of course it's going to be an exponential time problem, but already we have solved this problem, and if we know solution to this problem, can we use this solution to solve our problem? Yes, of course we can do. So the process is very simple. So whatever is unused in this, that means 2, 4 and 6 are unused. So let's use 2, 4 and 6 as our vertex covers. And now let's see, are we able to cover all the edges? So with 2 this edge is covered, with 2 this edge is covered, with 2 this edge is covered, because of these 2 this edge is covered, with 4 this edge is covered, this edge is covered, this edge is covered, this edge is covered, and because of 6 this is already covered, this is covered, this was already covered, this is covered. Now if you look at it, this edge covered, 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 this edge covered. All the edges are covered just by using 2, 6 and 4 as the vertices, which are called the cover vertices. So using this vertex cover, we can see that all the edges are covered. So how did we get this? We just transform this information into this. How do we do? So whatever is not used is used here. So what does that say? So there are vertices 1, 2, 3, 4, 5, 6 and 7. And for independent sets, what are used? 1, 3, 5, 7 are used. Now for our vertex cover, what are we using? The other things. So this we are using, this we are using, and this we are using. 2, 4 and 6, which are not used in the independent set, are used as vertex cover. So how much time is required? So if there are n vertices, so if this is used, so this is not used, this is not used, so this is used, this is used, so this is not used, this is not used, hence it is used, this is used, not used, this is not used, so used, this is used, hence not used. So there are n vertices. Then to identify how many of the vertices can be this, so this what do you call independent set converting to the vertex cover, we are doing in order of n. This conversion we are doing in order of n. So somehow we could make out that these are the 4 nodes, vertices, which are part of independent set. Then all the remaining will be part of vertex cover. So that way we can solve this problem by knowing solution to this problem. So in polynomial time we could solve this problem. Okay, how about this? So now as far as the click is concerned, now just take a bar. For click, consider a bar. That means the opposite of the adjacency matrix, you use it. So 1 to 3, 1 to 4, 1 to 5, 1 to 7, there is no connection. So from 1, 3, 4, 5, 7. So from 1, 3, 4, 5 and 7. From 2, 4 and 5. From 2 you need to connect to 4 and 5. Okay, from 3, 1, 5, 6, 7. From 3, 1 is there, 5, 6 and 7. And from 4, 1, 2, from 4, 1 and 2 are already connected. From 5, 1, 2, 3 and 7. From 5, 1 is connected, 2 is connected, 3 is connected and 7. And then from 6 it is 3 and 7. So 6, 3 is already connected, need to connect to 7. And from 7 all 1, 3, 5 and 6. So 1, 3, 5, 6 all are connected. So now you try to identify what is the maximum click possible. The maximum click possible is the one which we had identified as our this, what you call 1, 3, 5 and 7. If you look at them, 1, 3, 5, and 7. So if you look at the click, it says 1, 3, 5, 7. So from 1 to 3 there is connection, from 1 to 5 there is connection, from 1 to 7 there is connection, 3 to 1, 3 to 5, 3 to 7, 5 to 1, 5 to 3, 5 to 7, 7 to 1, 7 to 3, 7 to 5, all are perfectly interconnected. So we have a click of size 4. So what we did, we just found the complement of the adjacency metric and drawn that, and already we were knowing that these are the 4 positions where these nodes are there, which are part of independent set. So the same information is used and said that these 4 together will form a click. So what we did, so how much time is required to find complement? So definitely this complement we require order of n square, and that's it. So this conversion from the independent set to the click problem is done in order of n square, which is again polynomial time. So we can say that if one is known, through reduction we can find solutions to other in polynomial time. So that's the reduction. And another important thing we would like to talk now, in this particular case, the independent set can be converted into vertex cover, independent set can be converted into a click. Therefore, we can say that this independent set has a special property. It is NP, and also you can make sure that it can be converted into all others. So we can say that it is NP complete problem. So this way we can claim that it's a NP complete problem, because using a solution to this, now I don't know how this solution is made available. So maybe by magic, or maybe by some random assumption. So when it's a random, then definitely it is non-deterministic. So if this problem is solved in polynomial time, then definitely some non-deterministic approach was used. So whatever, if this solution is available to us, then we can verify that in polynomial time. Therefore, this problem is NP problem. Then this problem can be converted into other NP problems, and its solution will lead us to the solution of other NP problems. Therefore, we can claim that this problem is an NP complete problem. So that's one example about NP, NP complete, and reduction. Thank you.